Hello, everyone. Welcome to this webinar. My name is Namit Singh. I'm working with Exebenus as World's Digitalization Manager. Thank you for taking time out of your schedule to join us today. We are hosting this webinar from Exebenus office in Stavanger, Norway. We have audience from several geographical locations, as I can see, and I'm pretty sure many of us are still working from home due to COVID-19. I hope you and your families are doing well and staying safe. Today, we are going to show Exebenus Pulse machine learning agents that help predict stuck pipe conditions, thereby increasing productive time and reducing NPT related to stuck pipe. Duration of this webinar will be approximately 30 minutes, including the Q&A session. I'll start with a short introduction to Exebenus and our machine learning agents for predicting stuck pipe. We will also demonstrate few field use cases of Exebenus Pulse machine learning agents. And through this demo, you'll get an understanding of how machine learning agents assist real-time operations and break through in identifying stuck pipe conditions, thereby reducing NPT. At the end, we will close out with some Q&As. So firstly, let me tell you a little bit about Exebenus. We are a company that focuses on digitalizing drilling and completion operations. Our main goal is to present operators, service providers, and rig crew with solutions that promote consistency, standardization, and predictive technology to reduce non-productive time and act as an automation enabler for rig operations. Our expertise is focused on the drilling and wells domain, and of course, our software architects and developers are available to facilitate a solution with an open API to enable integration with the various work processes or workflow you may have. During this webinar, you'll also meet Dalila Gomez. She's our machine learning project lead, and Jan Koregelan. He's our principal product manager. So let me give you a high-level view of Exebenus Pulse and our machine learning agents. Exebenus Pulse is made up of two modules, build and run. Build is where an end user, which could be a drilling engineer, drilling supervisor, or a completions engineer profile, they are building the digital operating procedure and assigning it to the string or BHA, and same could be done to a phase or section within a well bore. So Exebenus Pulse produces digital operating procedures that can be viewed either on a PC or tablet mode and also printed in PDF format. When we talk about the run module, these digital operating procedures are connected to WITSML data stream for an automated operational tracking. The driller can also access these procedures digitally, either on a tablet or on a PC for tracking and validation. If you would like to learn more about the Exebenus Pulse build and run modules, I would recommend visiting our YouTube channel, where we have posted videos explaining these modules. In addition to these modules, the Exebenus Pulse solution contains machine learning agents. That's the topic of today's webinar. These agents analyze data to predict hazardous situations and notifies the user of the changing conditions and potential issues they may cause. So the question arises, why are we focusing our machine learning agents on stuck pipe at the moment? And there are plenty of papers discussing this topic and potential technologies to reduce stuck pipe conditions or predict stuck pipe scenarios. What we are going to show you are some new commercial machine learning agents that help you predict and preempt the situation using readily available parameters during drilling operations. One of our clients see approx 10 to 12% of total NPT attributed to stuck pipe, and they are aiming to reduce this by 5 to 7% over a year by using our machine learning agents. They have been using Exebenus Pulse machine learning agents since first quarter of 2020 and have already seen significant reduction in NPT associated to stuck pipe. We'll show you examples for these machine learning predictions as well. In this webinar, we'll showcase anonymized data from Petronas, our technology partner for machine learning project. Presently, we have 3 machine learning models commercially available for deployment, namely differential sticking, wellbore geometry, and lastly, hole cleaning. These three standalone machine learning models are supplied within one package, assisting in solving different stuck pipe scenarios. So let me introduce you to Dalila Gomez, mentioned earlier. She is our project lead for machine learning here at Exebenus.
Thanks, Namit. Hello, everyone. This is Dalila speaking. I'm going to give a brief introduction about myself. Before joining Exebenus, I've done a PhD at the University of Stavanger within drilling, simulations, and numerical models. As part of the machine learning project, I have combined both engineering and data science knowledge for helping to create Exebenus Pulse machine learning agents. Before that, I worked in an operator as a project engineer in an EPCI project. Exebenus Pulse machine learning provides early indications of stuck pipe. Our warnings and alarms are triggered based on the predictions to give the drilling team enough time to act and avoid the stuck pipe. Currently, we have 3 models running in real time for drilling operations: differential sticking, hole cleaning, and wellbore geometry. For the differential sticking, the predicted parameter is the hook load. Research have shown the existence of a specific hook load signature, which indicates potential differential sticking. The hole cleaning model relies on ECD predictions. And by analyzing the data, we have seen that predicting the ECD pattern is an early indication of hole cleaning issues. For wellbore geometry, we combine the hook load predictions and the dogleg severity ahead. We can predict early signs of few types of wellbore geometry, including ledges and stiff BAJ. In the next slides, I'm going to briefly introduce the concept behind each agent. For the differential sticking model, we predict the hook load ahead. The basic idea here is to monitor the force necessary to overcome the static friction after a connection. As you can see illustrated in the figure, it starts from the red dot. After collecting data from few stands, we start predicting the pattern for the next stands. Warnings or alarms will be triggered if the predicted hook load seems to follow the signature compatible with differential sticking. It's important to highlight here that our machine learning model is not a classification model, which means that our outputs are not stuck and not stuck. We provide warnings and alarms to alert that if the operation continues as it is, a potential stuck pipe may occur. The warning is provided early enough to allow the driller to act and avoid the event. As real-time data comes in, the prediction curve will be updated. So for instance, if there is a warning and the driller takes action, the warning should stop. For the hole cleaning, the parameter predicted is the ECD. And this is an example of the type of signature that caused our model to react. So this is a case where there were hole cleaning issues. On the top lane, we can see a short part of a drilling operation where we can see the drilling and the reaming part. On the bottom, the numbers in blue show the ECD variation during this time. The vertical yellow bars are warnings provided by our software. The risk of wellbore geometry stuck pipe also utilizes the hook load prediction. When an increase in drag is expected, and in addition to that, if the bit is moving towards a high dogleg severity zone, a warning or alarm will be triggered, depending on the severity expected. For tripping in, we scan the DLS below the bit, and for tripping out, we scan the DLS above it. And this is how it works. The training process is illustrated on the top. First, we analyze the historical wells and select the proper data for training the model. The model is then trained with real-time data, both from normal operations and with stuck pipe scenarios. Our machine learning models are classified as supervised machine learning, which means that the machine can learn how the different parameters behave in different scenarios. The training data goes through a pre-process stage and then is used to train the model. After training, we test the model performance and tune it. And this process might happen several times until we find the local optimal configuration of the machine learning model. Our model is based on the neural networks approach, and it has shown that it can achieve quite good performance with a low amount of training data. Well, at this point, the training models learned how the predicted values behave, for instance, ECD or hook load in our case, based on the training set provided. The model is then deployed in the server for the client's use. As shown in the process illustrated in the bottom, our system reads the sensor data from the WITSML server, pre-process the data, and feed into the trained machine learning models. The output will be pushed back to the WITSML server and will appear as a prediction curve to the user. We can always update the training set by, for instance, adding more data to the existing training set, for instance, a new well. And an interesting fact about this type of model is actually that the more training data we use, the more accurate and robust the model becomes. Therefore, the model is continuously improving over time as more data is available. Well, here you can see an example, what I mentioned in the previous slide. The output is seen to the user as a prediction curve. In this figure, you can see in red. So this is a differential sticking model when monitoring real-time operation. So the hook load predictions are in red, and the past predictions are stored, as you can see, in the green curve. The past predictions can be used for calculating the accuracy of the predictions in the end of the run. In this case, there were 3 warnings and 1 alarm to advise the monitoring team to be extra careful with potential differential sticking ahead. The philosophy behind Exebenus machine learning is to have simple machine learning models working together instead of one complex model that is fed with all the parameters available. This is found to provide more accurate results, and we can also have more control over each model. After creating the concept and developing the code, our models are deployed in the IBM cloud. In this table, we can see a summary of the models. For the differential sticking, the criteria for warnings and alarms are function of drag and standstill time. The predicted time is between 30 minutes and 4 hours ahead. In the last column, you can see the input parameters required. For the wellbore geometry, the criteria includes hook load signature and dogleg severity, and the prediction window is roughly the same as for the differential sticking. And finally, for the hole cleaning, the warnings and alarms are based on the ECD predictions that are triggered between 30 minutes and 1 hour ahead. Now I'm going to pass the mic to my colleague, Jan Kore, who will show some practical example cases.
Thank you, Dalila. Yes, my name is Jan Kore. I have a master's degree in petroleum technology and have a history since the 90s. Started off in Baker Hughes as a LWD operator in North Sea and Gulf of Mexico, and had various positions in Baker and before I joined Kongsberg Digital, and been very heavily involved working with WITSML data and the real-time data in the drilling domain. So our aim has been all the time to keep it simple, use the available data at the different clients, and most of the clients have WITSML data, so that's why we started on that. And we actually take out the surface parameters, which we see here in the picture at the top. Block position, standpipe pressure, mud flow, RPM, the normal parameters we use. And we use that as an input to the model, and then we feed back in the same time-based data as a curve, in this case in the dotted blue curve at the bottom, and also using the normal features you have in the WITSML viewer, in this case the Cycling Discovery viewer, or it could be another viewer from other clients. So now we'll start the sequence here, and we'll see that the data is taking in. At the top, we see there's a last updated value kind of indicating the model is running. And we see the bit depth and hole depth updating as we go along. And there's some traffic light indication at the top. In the middle track there, we'll see the prediction of the black curve. This is kind of the historical one. And the purple one is the prediction ahead of time. And we see the real-time data coming in, ticking along. And the prediction is updated approximately every stand. So then the prediction will kind of move ahead. And we also have a status track to indicate the color, or kind of a traffic light indication of where is the status is. And we see now we have a low to medium risk of hole cleaning issue. And this is kind of the model detecting the relation between the flow and the standby pressure. They are getting a bit off. And that's how we can indicate a warning by using the existing alerting system in the viewer, by flashing and sound, and also indicating in a track with a yellow bar and a traffic light indication. So, and the next example will show a tripping scenario. We're tripping in, and here we see when we start the sequence, now that the data is ticking in, we see the real-time data being updated, and we'll pay attention to the different sticking model in the middle. We'll see the prediction, the red prediction ahead of time is now dripping and dropping, and this is because we have a buoyancy effect in the mud. And we'll see that soon we will have a low to medium risk of differential sticking, warning us every joint as we go in the hole, and because of the decreasing trend in the drag in this case. And we also say then we come with a potential risk. So we create these kind of text to help the end user to explain what it is. And what they did actually here, then we start filling up the pipe to avoid this buoyancy effect. And now they increase the flow in the mud to make sure that we get some, avoid this buoyancy effect. And we also see the prediction stop, and now it updates again because the connections were not in place. Now you see the predictions going ahead. And in a tripping phase, it's normally we see that we can predict approximately 10 joints, 10 stands or 10 joints, depends if it's casing or running with pipe, ahead of the bit. So that's in this case, it's approximately, depending on the speed, of course, how fast we're looking forward. And the drilling is approximately 1 stand ahead. We do the prediction.
I'll summarize by mentioning that these models are commercially available for deployment. This means if you have VidSimil data for your ops today, our models are pretty much plug and play, meaning VidSimil in and VidSimil out, including our machine learning predictions, including alarms and warnings Jan Kåre demonstrated just now. They are installed as a single package, but their functionality is totally independent of each other since different parameters govern each model. And lastly, these models require limited wells data for training. If you would like to test our solution with your wells data, please contact us at info@exebenus.com. Let me just mention the Exebenus YouTube channel is out there for you to explore and find out more about our products. At the same link, we will share the recording for this webinar. I'm going to go ahead and close out the session. Thank you everyone for joining. Hope to see you around next time.